Good evening, everyone, or good afternoon, or good morning, because this is a webinar, so you may be from all parts of the world. So I'm telling you to all of you, good morning, good afternoon, and good evening. My name is Roxandra Sepoy. I'm part of EURADOS, and today I will be a moderator for the 27th EURADOS webinar with the following topic: neutron dosimetry, basics and applications with PADC track detectors. Little things about EURADOS. EURADOS was established in 1982 as a non-profit association for promoting research and development and European cooperation in the field of the dosimetry of ionizing radiation. There are more than 80 voting members, institutions from 31 countries represented by designated individuals, and also there are more than 700 associate members, scientists working within the 9 working groups and contributing to the overall EURADOS mission. You can check out more about EURADOS using the EURADOS link, and you can see sign up for the newsletter and receive all the news regarding our publications and our reports. The goal of EURADOS is to promote research and development and European cooperation in the field of dosimetry of ionizing radiation. And the main activities are the coordination of the working groups, promotion of technical development and implementation in routine work, contribution to compatibility within Europe and conformance with international practices, and also organization of scientific meetings and training activities, organization of intercomparisons and benchmark studies. Also, EURADOS issued the strategic research agenda, visions for radiation dosimetry over the next 2 decades. You can check out the latest publication, the second edition, which was published in 2020, and see all the visions and all the that EURADOS is seeing over the next two decades. The 9 working groups that are organized within EURADOS cover a lot of various topics in the dosimetry field. There is working group 2 with harmonization of individual monitoring, working group 3, environmental dosimetry, working group 6, computational dosimetry, working group 7, internal dosimetry, working group 9, dosimetry in radiotherapy, working group 10, retrospective dosimetry, working group 11, high energy radiation fields, and working group 12, dosimetry in medical imaging. And the newest working group in EURADOS family is working group 13, lucky number, dosimetry in nuclear medicine. You can find all the necessary information on the EURADOS website, and also you can see the email address of the working group chairs, and you can contact them if you want to attend the EURADOS annual meeting, join some working groups plenary meetings, and get in touch with them if you are interested in their working group tasks. This webinar will focus on one of the tasks within working group 2, harmonization of individual monitoring. This working group focuses on harmonization of individual dosimetry services procedures, and not only, also training courses. And within this working group there are several tasks. There is the learning network, which is organized at every EURADOS annual meeting. It is intended to share and discuss hot topics faced within the community. There is a training task led by Kinga and Liam, and this task has the mission to set up a DosiLearn exchange program within the staff of individual monitoring services. There is also a task on data management in dosimetry led by Robert, in order a task with the aim to identify data and IT problems. Also, the training course, which is one, let's say, of the oldest tasks, with a training course on RP 160 recommendations, and it's almost a yearly training course. Next one is programmed for spring 2026. And also a task that is focused on a survey on routine practices within the individual monitoring services that would be useful to as reliable inputs to help writing 2 new ISO standards. This task is led by Violeta. CR-39 quality task. This task intends to address the issues of the CR-39 detectors in order to improve and harmonize neutron dosimetry performed with solid-state nuclear detectors, and the intercomparison organizing group of this working group. Within this task, regular intercomparison exercises are organized in order to provide individual monitoring services a method to show compliance with ISO 17025 requirements. The webinar, as I said, it will be focused on one of the tasks of Working Group 2 and is focused on the results from the CR-39 quality task. The webinar will be focused on basics and applications with PADC track detectors. Why? We thought about this webinar because, as you know, all know, neutron dosimetry is a challenging task. Many types of instruments have been developed for neutron detection and measurements, like albedo dosimeters or track detectors, and each with distinct advantages and limitations. Track detectors made of PADC, also known as CR-39, represent one solution with many advantages, like they are lightweight, cost-effective, and easy-to-operate devices, and they can provide a high sensitivity in a wide range of workplace scenarios. But as you know, there are still some issues, and this webinar will address these issues hindering the performance of PADC. As lecturers, we will have Dr. Matteo Bolzonella. He's a physicist. I'm very proud to present him because he was the leader of the CR-39 task within Working Group 2, and also he received the EURADOS Young Scientist Award this year in Bucharest for all his work done within Working Group 2. And also accompanying Matteo is Dr. Eduardo Yukihara. He's the head of the radiation metrology section and dosimetry group. Also, it's an honor to present him because all the nice stuff that you find on luminescence and passive dosimeters are written, the papers are written by Dr. Yukihara. Both of them are from the Department of Radiation Safety and Security from Polscher Institute from Switzerland, and they will present you this webinar. They will start with fundamentals on neutron dosimetry, continue with routine neutron dosimetry, then enhancement of neutron dosimetry with PADC, and also then at the end some conclusions. You may write the questions in the chat, and me and all the organizing committee, Francesco, Kirstin, and Joanna will be here to check out all your questions and bring them forward to Matteo and Eduardo. I wish you to enjoy this webinar. Thank you. Please, Matteo, Eduardo.
Share the presentation. Can you hear us?
Yes, we can hear you.
Perfect. So yeah, thanks a lot for the kind introduction. Matteo and I will share the presentation. I mean, most of the work was done by Matteo, also the preparation for the slides, but we decided to add this short introduction. So we'll switch a couple of times the presentation during this next 30-40 minutes. Let me advance here. Oops. Have to use this? Oh. What about the pointer? Can I use the pointer? Pointer options, okay. So you mentioned already about this the outline. The core is part 3, of course. That's the work of Matteo, but we're going to give a short introduction on the fundamentals and a little bit of the routine use of PADC, particularly here at PSI. So in terms of the fundamentals, the challenge of neutron dosimetry, you mentioned some of them already. We're dealing with a very broad spectrum of energies. So while in photons we're dealing with tens of kiloelectron volts up to mega electron volts, here we go from milli-electron volts all the way to hundreds of mega electron volts. So it's a very broad spectrum in terms of energies. Not only that, but the spectrum not only varies according to the source, but they can also be changed due to the backscattering, for example, from the walls, or scattering from the walls, from the body of the person. And therefore, the detector, the dosimeters, will see different spectrum depending on the angle as well. We're going to explain a little bit more where this comes from, but all the neutron detectors, they have strong energy dependence. There's no neutron detector that has a flat response respect to the dose equivalent, for example. So just an example, I give here the response for albedo detectors as a function of neutron energy, and of the PADC detectors that we're going to be discussing also as a function of neutron energy. And another complication is that the fluence to dose conversion factors, they vary also by orders of magnitude as the energy of the neutrons change. And you see here that they increase a lot, about 0.1 mega electron volts. So the region that's most important for dosimetry, let's say that the contribution to the dose according to the fluence to dose conversion factors is higher, is this region here. And if we mark this region in the other graph that I show you, you see that that's the region where these peaks are, for example, for this spectrum. But it's also the region where the albedo detector starts to fail in response, and is a region that's covered by PADC, but up to a certain point. We don't see, PADCs don't see below this energy or above this energy either. Or even in this range, the response is small. One of the challenges to start with neutron dosimetry is the fact that it has different interactions. So the neutrons do not deposit the energy directly into matter. They deposit energy through different process that creates charged particles, and these charged particles deposit energy in matter. So it's an indirect type of ionizing radiation. And each one of these processes have strongly also energy-dependent cross-sections for interactions. And they will produce particles that sometimes will be seen by the detector, sometimes not, depending on the characteristics of the detectors. So just for an example, some of the interactions that we take advantage of. For example, absorption. That's a nuclear process where the neutrons captured by, for example, lithium-6 or boron-10, and then you get a tritium and an alpha particle being emitted, and these are charged particles that deposit energy in the detector. These are the principles used, for example, for TLD albedo detectors and some of the bubble detectors that contain some of these isotopes, I think lithium-6 or boron-10. Now, the cross-section for this interaction decreases rapidly with an energy, with the square root of the energy, actually. So this type of detectors, they are mostly sensitive to the low energy neutron part. Now, the fact that they see this low energy part means that they see not only the low energy part of the direct spectrum, but also of the scattered spectrum. And that's what the albedo detectors make use of. The albedo detectors essentially detect the neutrons that are moderated and backscattered from the body. And the response for this type of detectors is not this one. This is the response just for there's a cross-section for the interaction. The final response of the detector is a combination of other elements and can be, in this case, like this for albedo detectors. In the case of PADC, for example, we use the scattering. So a neutron comes and pretty much kicks a proton from the hydrogen. And what we use here, but also used in some of the bubble detectors. The cross-section for this elastic scattering follows this profile here. But again, at the end, the detector response is a combination of that and all the process that happens after that. So this process will generate recoil protons. But if the proton has too high energy, it's not visible. If it has too low energy, it may not reach your detector. So at the end, the response of your detector will be something like this, which represents the optimal region where there is a sufficient nuclear interaction and we can see the product of these reactions. We're not going to discuss here, but just for completeness, there is also other process that can be taken advantage of. For example, fission. This was used actually in some personal dosimeters, even here at PSI, more than 2-3 decades ago. These detectors, for example, contain uranium and thorium foils. And when the neutron interacts with this thorium, it creates also a fission, and you can record these tracks in a thin plastic foil. The cross-section for this interaction starts at a few MeV and is more efficient above 3 MeV. So we detect the byproduct of the neutron interaction with the detectors or converters. The signal can be, for example, the luminescence proportional to the absorbed dose. That's the case of the thermoluminescence albedo detectors. It can be tracks created by the passage of a heavy charge particle, PADC or fission track detectors. That's what we're going to discuss more in detail here. Could also be bubbles created by the passage of this heavy charge particle in the bubble detectors. So how we count this can be different, but we're always measuring charge particles created by the neutrons. Now, summarize a little bit the neutron dosimetry challenge. So we have, again, indirectly ionized radiation, a wide range of interaction mechanisms with matter. We didn't mention here, but typically we are dealing with mixed fields. That means neutron plus photons or neutron gammas. If your detector is also sensitive to photons, that will create a problem. The energy spans more than 12 orders of magnitude. They show a wide range of angles of incidence. So normally you're not dealing only with the neutrons from the source, but they are scattered and come at different angles. The fluid to dose conversion coefficients vary a lot in this energy range. And as a result of all of that, the neutron dosimeters, they show a worse lower detection limit compared to photon detectors and a worse angular response as well. We're going to go in more details here. Now I'll hand the word to Matteo, who will explain the basics of the PADC detection.
Thank you, Eduardo, and good afternoon, everybody. So PADC stands for polyallyl diglycol carbonate, and it is a plastic polymer with the chemical composition that you can see in the formula in brackets. It is also very well known with the brand name CR-39, that stands for Columbia Resin number 39, after the original product patented in the 40s by the Columbia Southern Chemical Corporation. For dosimetry application, PADC detectors are sold as sheets with about 100 detectors in each of them. And concerning the production process, PADC is typically polymerized by using these monomers, these allyl diglycol carbonate monomers, in the presence of a specific initiator. And during the process of polymerization, the double bonds of the allyl groups of the monomer opens to form a cross-link among the polymer chains, obtaining a thermoset resin. And additives can also be used to enhance specific properties of this polymer. The whole production process takes about 20 hours, and it is known as cure cycle, and it involves various steps at different temperatures. If you look at some physical properties of the polymer that you can see here in this box, so we have low density material with a refractive index that is similar to that of glass, and it is a polymer transparent to visible light. So you can immediately understand why this polymer is one of the most common alternatives to glass, for example, for the manufacturing of optical lenses and glasses. Coming to the dosimetry application, the use of PADC as a radiation detector has a long history, and it dates back to the 70s to the studies of Cartwright, Shirk, and Price. Concerning neutron dosimetry, here you can see a sketch of the working principle, And so we start with let's say, a high LIT ion that traverses and breaks the polymer chains of PADC by ionizing the bond, and so breaking the chemical bonds and producing chemically reactive species like radicals in a narrow region along its trajectory. And this region of damaged material is known as latent track. Latent because it is hidden. In order to become a proper track, we have to enlarge it and fix it into the material. And this is done via a procedure known as chemical treatment, etching, where the polymer is inserted into a chemically aggressive solution that in fact enlarges and fixes the track in the polymer, obtaining a track that has the aperture of some microns, and so that can be seen under common transmission light microscope that can be found in pretty every laboratory. And then you can observe, discriminate, count these tracks and convert them into the dosimetric quantity of interest using proper calibration and analysis method. Note that in the case of neutron dosimetry, the high LIT ions produced in the tracks are mostly recoil protons from elastic scattering on hydrogen. Coming a bit more into detail about the track formation mechanism, let's focus on this simplified sketch. So we have our high LIT ion in blue that traverses the polymer and produces the latent track. Then we immerse the polymer in our etching solution, that is in this case an aqueous solution of sodium hydroxide. And here we have the start of the erosion of the etching process. It is crucial to note that we have two different speeds of erosion. One that is known as bulk etch rate, that is the erosion speed of the bulk material, the undamaged one, and another one that is known as track etch rate, VT, that is the erosion speed along the latent track, and so the damaged polymer. Since here we have damages like reactive species, here we have the erosion that proceeds faster, and so VT is greater than VB. And this is crucial for the formation of the track that is formed as a cone with this shape. And then we can remove from the solution the polymer, and we can analyze our track introducing some geometrical quantities, for example, the diameter of the track opening, or H, that is the depth, the thickness of the removed layer of bulk material. And note that the track formation mechanism is pretty much similar to what happens on the surface of water when you have moving objects, like, for example, a ship or a bird swimming on the surface of water. Here you have some other hints about the track formation and the track appearance. You have also an animation of the track growth. And I want just to mention that, of course, the track opening can be circular or elliptical, depending on the tilting of the particles that produces this track. And these tracks appear as black circle or ellipses under the transmission microscope because of light reflection and refraction on the conical wall of the track. It is crucial to mention that for the formation of the track, we have a condition to be fulfilled that is related to the tilting of the particle with respect to the detector surface. So it is not sufficient that the erosion speed is higher, and so the erosion is faster along the latent track. But what matters is that the depth reached along this track, and so in the polymer, is greater than the depth of the thickness of the removed layer of bulk material. And so we must have a trace on the post-etch surface, that is to say that the track 8 must be greater than 0, as you can see here in this formula in green. And with a bit of goniometry, you can invert this formula and obtain a condition for the track angle, that is theta here in blue in this sketch, that must be higher, greater than theta c, known as critical angle, that is equal to the arc sine of VB over VT. Getting the condition to have a etchable and detectable track. So first of all, the average LIT in PADC of the ion produced in the track, in particular along the track, must be greater than about 10 kiloelectronvolt over micron. Then the dip angle must be greater than the critical angle. The etching process shall not last for too long, otherwise you kind of wash out the track that becomes no more a cone, but a sort of hemisphere, and you lose contrast, and so you lose the information that can be useful for dosimetry application. And so let's say that the removed layer of bulk material should be about 10-15 microns. And finally, the track dimension must be big enough to be observed under the microscope, and this typically happens if the track length is greater than about 1 micron. Now I leave the floor again to Eduardo for some information about routine neutron dosimetry with PADC.
Yeah, so I mean, what's the result of all of this in practice? In practice, so first of all, at PSI, we use our badge is something like this. It combines an RPL detector with the PADC detector below. The PADC is the one that Matteo described. We use polyamide as a radiator, so the neutron converter that produces recoil protons in the detector due to the neutron interaction. The etching takes place for almost 3 hours. And the system that we use for count is from Tassel image system in the UK. And the approach that we use is track counting, which means we simply count the number of tracks, and we convert this number of tracks to those using a calibration with a Mersenne source. Now, the challenge for the system, the dosimetry system, is always material defects to identify what's a real track, what's not a real track. So if you look here, there are several defects that can be seen in this image that Matteo chose. And if you do not have an algorithm that discriminates that, then this can be understood as coming from neutrons. So there'll be false positives. So you both can have false positives and you have unirradiated detectors, so control detectors with a higher number of counts, which we don't want. So to avoid that, there are several strategies that needs to be used. We need to reject bad sheets. We need to calibrate each batch separately, perform agent fading control or introduce corrections, and enhance this track discrimination approach in addition to improve the QA and manufacturing process of the dosimetry grade PADC, which was the goal of the test group that Matteo led. So in our program, we have several things that we need to do. We have acceptance tests of the materials. We have blind tests, routinely blind tests. We have control and calibration detectors prepared for each monitoring period and each customer. And we have also intercomparison exercise in which we participate. Just a few examples. As Matteo showed, these are the sheets of PADC that we obtain from the manufacturer. From these sheets, we separate, we sample the sheets. So some of the detectors are kept as blank, some are irradiated. And with that, we make a quality control of each sheet in each batch. These graphs show a little bit of the results. An example, here's the track density. So tracks per centimeter square for different batches and for within a batch for different sheets of material. The dashed line is our acceptance criteria. So we see that if the batches or sheets exceed a certain number of counts, then we have to reject them. The bottom one is the track density for irradiated detectors, also as a function of batch and sheets. And we see that sometimes they are not uniform. I chose this as an example. Sometimes you have batches that have almost a separation sometimes. So for example, this particular batch, we could use this one together and this one together, but we would try to avoid to mix these two together. This one is the same thing. Either we have to separate them or we have to send them back, depending on the more qualitative measurements of this acceptance test. As I mentioned, control and calibration detectors are prepared for each period. That's a photo of actually how this is organized in our laboratory. For example, each one pair of this is for one shipment of detectors for one of our customers, that's CERN. Within each one of this box, for example, these are the control detectors. We have several control detectors that were prepared together. So when the detectors come back from the customer, we take a few calibration detectors, a few control detectors, we etch them and we read them together with the detectors that were returned from the customer. So with these, we guarantee that the quality of the unirradiated detectors and the sensitivity that the detectors sent to the customers and the calibration detectors are the same. We recently compiled the results of the various intercomparisons that we participate. We participate in the EURADOS intercomparisons, and every year we also participate in the PTB intercomparison. And these are the results for different radiation qualities and for different angles. And we see more or less that they satisfy this criteria. These are for different angles. So for 60-degree, here we are in the limit of the acceptance for the ISO norm using this minimum detectable dose. If you decrease the minimum detectable dose, this can become even tighter, and this becomes more difficult to pass. So the main problem of the PADC, one of the main problems is angle response for this extreme angles like 60 degrees. The energy response we mentioned before, the energy response is essentially, so the detectors are sensitive between, let's say, 100 kV and 100 MeV, and that's because this combination of cross-section for the elastic interaction and the energy of the recoil protons and the range of the recoil protons. For low neutron energy, the recoil protons have very low range. They may not reach the detector efficiently. And for very high energies, they will have a very low linear energy transfer, very low LET, and they may not damage the track enough to make a difference between this track ratio and the track edge and the bulk edge ratio. Rate, sorry. Just for comparison, for albedo detectors, we have this different response, and if we put here a line with 1 MeV just for a reference, we see that these detectors are practically complementable. So the albedo are better for low energy, and the PADCs are better for high energy part. This is the angle response also from intercomparisons, and that's more or less what I mentioned before. So here for 60-degree, we have a response between 40 to 60%. Here it's difficult to say something because the dose was low, so this is a higher dose. But this shows the problem with the angle. And as Matteo explained, this comes from two different things. One of them is the critical angle of these recoil protons. So if they come at too steep of an angle, they will not be detected because they will be etched away. And also because the PADCs are planar devices. So also they have this angle dependence simply because of the geometry of the detector. With respect to fading, fading is the decrease in sensitivity due to this kind of repair of the latent track at room temperature while the user is wearing the dosimeter. We compile data from a customer for more than a year, and we see here that putting all the data together, there is a fading of approximately a little bit more or a little bit under 40% over a year. But there's also another effect that's aging, and aging is the worsening of detector material quality in time, resulting in loss of sensitivity. And it's observed when the detectors are stored for some time before use. Now, we did an experiment that combines this effect of fading and aging in one experiment, and this reflects more or less how we use the detectors here at PSI. Here, the detectors are prepared together, and in this experiment, they were prepared together and etched together approximately 1 year later. But they were irradiated at different points within this period. So this simulates the situation where you have a user with a 1 year, let's say, a monitoring period. We prepared, for example, the calibration detector at the beginning, and the dose that the user received can happen in any time during this period. And Matteo has also some data showing that the fading and aging have approximately similar rates, and therefore they compensate for each other. That means detectors that were irradiated at the beginning of the period, they do not suffer from aging, but they have fading. On the other hand, a detector that was irradiated at the end of the period, they do not suffer from fading, but they suffer from aging. Because the calibration detectors suffer then from fading, while the user detector suffers a combination of fading and aging, they more or less compensate each other. And you see here that we got more or less stable response over these 12 months. So Matteo will talk more about this later. In terms of minimum detectable dose, just using this track counting for fast neutrons, these are some statistics that we have for these irradiated detectors that we use in our quality assurance program. And here I plotted the minimum detectable dose, just basic estimation, because we have only, I think, 4 detectors per monitoring period. But I grouped all of them together, calculate averages for different monitoring periods and different times they were returned. And this is plotted as a function of number of months that they were in use by the customer. And we see that in average, we have less than 0.1 millisievert, but these are distributions. So there are some distributions that extend above that, and some batches show the higher minimum detectable dose. Now, this is again, the uncertainties in these are very large because we're talking about a small number of detectors, but the complete data shows a little bit how the detectors respond. In terms of linearity, they are pre-linear up to 100 millisievert. These are the deviations from linearity according to our requirement here in Switzerland. And if the dose is higher than 100 millisievert, as you see in these images here, so these are track images for 10 millisievert, 500, 2.5 sievert, and 5 sievert. The tracks overlap too much for counting, and then we have to start using another approach. And one approach is using transmission. So here we can take visible light and use the fact that the visible light is scattered by these defects, and the transmitted light then is lower. And if you measure the absorbance then as a function of the dose, you get a curve like this, which allows you to do dosimetry up to a higher dose level in emergency situations. So summarizing main advantage that was mentioned in the beginning, they were that each detector is relatively cheap. Of course, there's a high cost for quality management, quality control, quality assurance. But for the users, they are relatively cheap, they're lightweight, they're resistant, and they're versatile. And they are insensitive to photons. So if you have a mixed neutron gamma field, these detectors are not affected by the gamma dose. They have a good sensitivity and relatively high saturation dose. And the sensitivity is optimal in this region where the fluence to dose conversion factors increase a lot. And they are passive. They do not require any power supply. They do not have pile-up effects and no electromagnetic interference. There are, of course, limitations. As any passive device, they do not give any live indication. So we need to send the detectors for laboratory, for readout. Other types of detectors are recommended for cases where high dose or an alarm is needed. They are not reusable. That means once you use them, you have to throw them away. And this is, of course, a problem. On the other hand, once the detectors etch, the signal is there. So this can be read out or further analyzed in case of doubts. So if there's any issue with the dose or any question regarding the dose. They're affected by temperature. So if the temperature is very high, we see that this can speed up this healing of the tracks or even damage the plastic itself. For this reason, we store them in freezer prior to the use to slow down this aging effect. And we should avoid using the detector for extended period at temperature higher than, for example, 30 degrees to mitigate this fade. If no fading or aging correction is used, then we have to keep the intervals short. Otherwise, you have to use something like I showed you here before, prepare calibration and control detectors for each monitoring period. And we didn't have time to discuss here. Another option is also to try to enhance the response of the PADC by using converters not only for fast neutrons, but also for thermal neutrons. For example, here I show an example using polyethylene with 1% natural lithium. In this case, I have to remind you, we're relying on neutron capture processes. So the cross sections are like the ones I showed you before. They're mostly sensitive to low energy neutrons. Then we require an algorithm to combine these two signals. We should expect a large variability due to backscattering. So this signal part will be more dependent on what is happening to the neutron field in the neutron field. And if we use this, of course, we're reducing the area of each detector. So we need to use more detectors, or we're going to lose something. For example, the minimum detectable dose will not be as low as we expect. So this is an overview of the routine. I think I'll pass to Matteo to talk about the possible enhancements of the neutron dosimetry using PADC.
Okay, and I start with the EURADOS CR-39 quality task. This task started in 2020 within the activities of EURADOS Working Group 2 with the aim of improving the dosimetric performance of PADC material used for neutron dosimetry, mainly improving the material quality of the polymer itself. Moreover, we wanted also to share best practices and research findings in order to improve and harmonize neutron dosimetry with PADC in Europe and beyond. The task is conceived as a close collaboration among individual monitoring services, that is dosimetry laboratories, researchers, and PADC manufacturers. We have on board 20 people from the 9 institutions that you can see on this map, and I've been the task leader of this task, let's say, since the beginning to this year, and now the new task leader is Vendula Filova from the Slovak Technical University. We have on board also manufacturers. Here you can see the manufacturer that have participated to the task so far. And it is important to stress out the fact that these are among the most important PADC manufacturers for dosimetry worldwide. And they are participating in this task regardless their own performances, but to support the EURADOS research action in general. This is the, let's say, timeline of the task with the main steps. And so the first one was to involve PADC manufacturers to ask for sample material, to share, to disclose part of the quality assurance tests and details on the cure cycle, and also to ask for changes in the production process in order to test different recipes of material. Then we wanted to study the state of the art of neutron dosimetry with PADC, and we published a review paper that is available open access if you follow this QR code. And we wanted to highlight the best practices and also to find some inputs for the next steps of our research. Then we drew an experimental plan for some tests of PADC materials, focusing on background and sensitivity studies and aging and fading tests. We carried out these experiments using both monoenergetic neutron fields from accelerator facilities and radioisotope source fields. And we also intercompare different techniques and systems from different laboratories, highlighting relevant differences among the materials. Now, this is more or less where we are, and the next step will be to use these experimental findings to modify PADC, collaborating further with the manufacturers in order to reach this enhanced material, that is to say, a PADC material with a better quality for dosimetry. Briefly coming to the main experimental results of our studies. So we tested 5 different PADC sample materials, and we performed a study of the bulk etch rate, and we could identify essentially 2 groups of materials, let's say hard to etch and easy to etch, that is to say soft material with a higher bulk etch rate. And then we also analyzed the etch rate ratio, that is the ratio between VT and VB, using alpha particles from californium. And we found significant differences even for the same experimental condition, that is same particles, same etching, but we saw that some materials consistently show a higher V than the remaining 2. Then we studied the sensitivity. And for this study, let's say that we use the standard Polini etching technique that you can see here in this footnote, and we removed 15 microns of bulk material. And what is important, we adapted the setting for the scanning to each batch of different material in order to optimize the setting for a given batch of material to perform an unbiased scanning of this material instead of using some fixed settings that would work better for a material but worse for another one. And what we found, it was, of course, a difference in sensitivity for the americium beryllium quality among the materials, but also in some cases among batches of the same material. That is why a batch-specific calibration is recommended. On the other side, we didn't note a major difference in the energy response function of the various materials. We also analyzed the background, and we could find important differences among different materials and in general different batches. And so again, we recommend batch-specific calibration. And finally, we did some aging and fading tests with detectors stored up to 3 months at ambient temperature, pre-post irradiation with americium beryllium, and we found different behavior across material. So, for example, in one batch of one material, we had a decrease of sensitivity of 25% in just 1 month, while for other material, we have way less important impact of this aging and fading effect. And as Eduardo anticipated, we had a sort of symmetric trend, so aging and fading that behave similarly in terms of decrease of sensitivity. Now, passing to new method for track discrimination. Here, I want to just quickly present the method that I developed in the frame of my PhD. That is a novel track discrimination method based on genetic algorithm. That is a method that uses machine learning in order to optimize fast neutron dosimetry with the polytrack system. And this method has to be applied to each different PADC batch. So you start with a scan with the polytrack system of 2 sets of detectors, a set of irradiated detectors, detectors irradiated with americium beryllium, and background detector. Then let's say that for each object detected, the polytrack system stores up to 41 parameters, and focusing on 7 of them here, you can optimize the lower and the upper threshold for each one of these in order to maximize this function, and so in order to retain as much signal as possible and to discard as much background as possible. And this optimization is made through an iterative process that mimics natural selection, so that explains the name genetic algorithm for this method, and this is stopped once you find the optimum threshold for this parameter, maximizing this function, so this figure of merit. And just to show you very quickly visually the effect of this new method. So here on the first row, you have background objects and objects on irradiated detectors. On the second row, you can see the filtering of these objects according to the standard method of the polytrack that acts on a limited set of parameters, and it does it in a fixed way, so not optimized to different materials or to different batches. And so you can see that the average track density of irradiated detectors over the average track density of background detector, and so let's say the signal to noise ratio is about 8, while if you use this new method, you can reach a signal to noise ratio that is about the double. Also, we have some consequences on the energy response. So here you can see the same set of detectors scanned with a commercial reader that has image that is a sort of black box because you cannot really set and change the parameter for the track discrimination. And on the right, you can see this polytrack plus genetic algorithm scanning. And so you can see a flatter response, but also an increased response in the low energy part of this graph, where usually you have very small tracks that are discarded by the commercial reader because they can very easily be misinterpreted as background defects. Of course, AI is a hot topic, And so there are a lot of studies. Here we just cite a couple of them, but we want you to know that there are several other publications in the peer review phase. But we want to stress one important fact, that with any algorithm, it's important to show that the algorithm improves the whole dosimetry system. So it has to work for different doses, different angles, energies, and so on. And in the end, it has to fulfill the requirements from the standards. Coming to the last point, so extension to novel situation, I will just focus on one case study because we have a limited time, and I want to start it with some hints about the method that was used. So the track H rate, Vt, increases as the particle LIT increases, while Vb is fixed because it's a property of PADC, of the material. And so if you take the ratio, that is Vt over Vb, this is roughly proportional to the LIT, as you can see in this graph, when on the x-axis you have the restricted energy loss that for the particles and energy range of interest for neutron dosimetry can be taken as the LIT. But so if we can infer V from track morphology, and then we can correlate V to the LIT, that is in turn related to the energy deposited, we can use this information for dosimetry. And in fact, besides track counted method, and so the assessment of track density and then the conversion into the dosimetric quantity of interest, you can also perform dosimetry starting from LIT spectrometry. And so the average LIT along each track is assessed and then used to estimate dose equivalent in PADC, that is HPADC, with this formula where the LIT and also the angle of incidence of the particle generated at latent track are assessed through track morphology. The advantage of this method, that is more complex, is that it leads to a more stable response function, in particular with respect to neutron energy. And this method is applied in research, but it is also extended to ion dosimetry, for example, for space applications. In any case, either you calculate track density or this quantity HPADC, you have to apply calibration coefficients in order to get the dosimetry quantity of interest, that is H*10 for area monitoring or HP10 for personal dosimetry. Coming to the instrument used for this study, so we had both passive dosimeters that were built by coupling PADC detector with a block of PMMA that acts as a radiator, and so it increases the generation of recoiled protons and eventually tracks in PADC, and this was characterized experimentally and also using Fluka Monte Carlo simulation, and the signal was obtained using LIT spectrometry. On the other side, we had a passive rank counter called passive Linus, and here you have at the center a sort of sandwich configuration of two PADC detectors and an inner layer of boron carbide enriched in boron 10, so that the neutrons that come and are thermalized in this outer moderator shell can be captured by boron and produce alpha particles and lithium-7 fragments that generate tracks in PADC. And since the LIT of this particle is greater, and so it's greater the damage to the polymer, we need the same etching, but for a shorter time, that is about half of the time, to generate big enough tracks to be analyzed. And this is based on track density because, as you know, the signal of rank counter is intrinsically proportional to H*10. The experiment was performed at the CERN CLEAR facility, that is a linear accelerator of electrons with pulse beam, with structure that you can see here in the bottom right corner of the slide, and the maximum energy is about 220 MeV. This is used for experiments ranging from medical applications, so flash therapies, to material testing, for example, for space application. And we perform our experiment in this last part of the beamline near the beam dump that is called the in-air test area. We placed our dosimeters, 3 dosimeters on phantom in 4 position from 1 to 4, and the passive Linus in position 5, and all these were centered at the beam height. We used an electron energy of 195 MeV with a repetition frequency of 10 Hertz and 3 different levels of charge per electron train, 3, 25, and 50 nanocoulomb, so ranging from, let's say, standard condition to flash conditions. And we wanted to study the linearity of the devices. So if the integrated dose over the integrated charge is constant in these 3 configurations. Here you can see the results for the passive dosimeters for the conditions, the 3 conditions studies and the 4 positions. You can see a good linearity, so the ratio is quite constant for each configuration. And also, if you compare the experimental results with Luca simulations from the third RP team, you can see a very good agreement between measurement and simulation. And this proves that this instrument perform well in this kind of pulse environments. Coming to the passive Linus in position 5, here you can see a quite good linearity of the devices, but you see that from a signal that is about 5 millisievert on, we have track superposition that causes detector saturation. We can correct for this effect using a correction that mimics the one used for gaseous counters. And so we have this K, this correction coefficient, that has to be multiplied with the covered area, that is the area of all the objects detected on this PADC detector, that is a sort of space equivalent of the dead time of gaseous detectors. And if you use this correction factor and this correction for the signal, you can extend the linearity of the device up to about 20 millisievert. That being said, so we come to the conclusion. Neutron dosimetry is an intrinsically challenging task, mainly due to the variety of interaction mechanisms that neutrons have with matter. PADC offer a quite unique solution to this because they are lightweight, cost-effective, and they show a high sensitivity, in particular in the neutron energy of interest for workplace dosimetry scenarios. There are, of course, open issues, but we can improve them focusing on the hardware, and so improving the material itself, focusing on the software, and so improving the dosimetry method, the track discrimination methods, and so on, and also extending the application to novel and or challenging situations. All these points have been addressed during this webinar, and we expect that from present and future research studies from the extension of the application of this detector to new situation, and also from the follow-up of the EURADOS CR-39 quality task, this discipline will become even more widespread and effective. Here you will find the references of the studies that were considered for this presentation. And with this, we thank you very much for your attention. And of course, we are available for questions. Thanks a lot.
Thank you very much, Matteo. Thank you very much, Eduardo. Very interesting presentation and very interesting topic. We have some few questions. No, Joanna and Francesco, if you would like to help me and share the questions with Eduardo and Matteo. Thank you.
Yes, we have 2, I would not say questions, but comments from Rick Tanner. One says that the PADC with a thermal neutron converter can detect neutrons with energy below their fast neutron threshold. Do you want to say something more about this? It's just a comment, I think, yeah.
Yeah.
Then there is another comment, says, always from Rick Tanner. The neutron dosimeter from the UK Health Safety Agency uses sheet-specific calibration and electrochemical etching.
Sheet-specific calibration, wow.
Yeah, sheet-specific calibration. This is also a comment. Then we have a question coming from Mohamed Bakalem. How much chemical etching time is required to observe neutron tracks in CR39?
It depends on, let's say, the bulk etch rate and the track etch rate, but usually, and also, of course, on your chemical solution, because if the molarity is very high, then the time decreases, I would say, exponentially. Usually, if you use a solution of sodium or potassium hydroxide that are more or less 6 molar at 98 degree, you need something like 2 hours and a half, from 1:30 to 2 hours, I would say. For example, here at PSI, it's about 3 hours.
Okay, the same person asked another question. Can we count the tracks using Tasselmage?
The Tasselmage,
yeah.
Yeah,
If
actually,
the track development is done by the electrochemical method?
yeah, actually, I don't have experience with that. Do you know, Matteo?
I don't know. I know that the Polytrack system is being updated to do so. So probably with the Polytrack system, you can do this. I do not have direct experience with the task.
Yeah, I think I don't remember testing, at least during my period here. Maybe before it was tested. Maybe Rick Tanner knows more about it. But as far as I know, at least during my time here, we have not tested.
Okay, thank you. We have another question coming from ECR Sarasola Martin. Which is the storage temperature in the aging or fading pictures showed?
Yeah, these are room temperature. So we store them in the same place where we store our calibration detectors.
Okay, Rick Tanner also answered for the Talsmage questions, was adapted for reading electrochemical tracks, but it did not work well.
Yeah.
Okay, thank you for your answer. There are no more questions as long as I see.
No more questions, but we had quite a few. And
that's good.
Yeah.
Yes, and also a lot of thank yous for your presentation. So thank you very much.
We thank you for the opportunity and the attention from everyone on the other side.
Yes. Also, please stay posted to the EURADOS newsletters and LinkedIn social announcements, because we will have a new webinar on I think it's 27th of November. And also, don't forget that on Friday, on the 17th, is the deadline for the applications for the EURADOS Young Scientist Grant and Award. The grant consists of 4,000 euro that a young scientist can use for his research. So please apply. Also, the award consists in 500 euros, so it's good. So thank you again to all the participants and to you, Eduardo and Matteo. And let's stay in touch. Thank you.
Thank you very much.
Thank you very much. Thanks, everyone.
Goodbye.
Bye-bye.
Bye-bye.